In this video, I want to start building up some intuitions about going from the behavior of individual muscle fibers, which is what we saw over here with these graphs, to the behaviors of entire muscles and even muscle tendon units. And I'm going to do so hopefully by, without getting too much into the actual physiological structure of muscles and making more of a geometric argument here. Because this is how people originally built up intuitions about the function of muscle, and many of our muscle models that we use today to understand the behavior of muscles actually are not explicitly reliant on the microscopic structure of muscle. So we talked about how muscle fibers have this capability to produce force, and that force depends on their length and the velocity that they're moving at. And we also started this whole unit with this mystery of the flexing your bicep in the bucket of water experiment, where your muscles don't actually change their volume. They produce force and they shorten, but they don't change volume. And hopefully we'll be able to solve that mystery by building up this very simplistic but useful model of a muscle. So what I have here are some muscle fibers arranged in parallel. Muscle fibers right here. And this is like the origin point of the muscle. Just think of this as like a thick, really strong piece of tendon. And then the tendon itself goes off like this down to the insertion point. So here's the body of the muscle, got some origin and then insertion down here. Now let's think about what's going to happen when these muscles contract. The first thing to notice is that these muscles are at an angle. So they're oriented at some angle like this. Turns out this angle has a very important name and some very important properties, which we'll get to in a later video. But what's going to happen when these muscles contract? Well, depending on their length and depending on their velocity, they'll produce some amount of contractile force. It'll go like this in each of those muscle fibers. And here is the model, or the way to think about this behavior of this whole muscle tendon unit. We're going to think about this part down here, the tendon, as sliding back this way. So this won't be a perfect visualization, but maybe I'll show you roughly what I mean. To imagine, imagine when these muscles contract, this part slides back like this. Now what's going to happen when that happens? Well, first off, these muscle fibers won't be oriented like this anymore. They'll go from here to being more straightened out. Maybe the best way to draw this is like to leave them on and say that now the muscle fibers will be oriented more like this. So that angle that I drew earlier will change. The muscles will, of course, be shorter, right? Or the muscle fibers will be shorter because the distance from here to here, like that distance, is clearly less than the distance if you move this over here, right? Because then we'd be talking about this distance. So the muscle fibers change their length, certainly. And what's a consequence of that? Well, here's one. If we think about the total area, like let's say the surface area. Now we're not talking about cross-sectional area here. We're talking about this area. Is that total area going to change? I'm going to need to bring in a little bit of geometry here. And I'm just going to use the formula for the area of a parallelogram, because that's what the area that the muscle fibers are in is. It's like this parallelogram, right? With like this base and this not angled, but this height. Maybe you remember from geometry, area of a parallelogram is just base times height. which has this happy consequence of the area that these muscles occupy not changing as a function of where the tendon is, as long as it's sliding back and forth like laterally like this. So what does that imply? Well, number one, it implies that there's this mechanism by which muscles can contract and shorten a whole muscle tendon unit without changing the volume of the muscle fiber. And it also, maybe more importantly, other than solving our kind of interesting little mystery, it also introduces this extremely useful way of thinking about muscles, which is having, and maybe I'll draw it like this, having fibers oriented like this that have, number one, some length, and number two, are oriented at some angle, which we'll call, usually the symbol people use is alpha, but the name for this is the Pinnation Angle. I think the name for this comes from some Latin word that means feather. You'll notice that just like a bird feather has little like strands that come off like this, muscles also have these pinnated fibers that come off at an angle. And as we'll see in the next video, there are a couple different types of pinnation that we see in muscles. And we'll go in detail about that in the next video.